Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the Sky and Telescope series. And I am very happy to have Sky and Telescope author Emily Lakdawalla with us today. Hi, Emily.
Hello. Nice to see you.
Good to see you. Where are you at, Emily?
I'm here in Los Angeles, California. It's a beautiful hot day today, actually.
Ooh, very cool. I'm in Phoenix, and it is definitely a toasty day. Probably in another day or two, we'll tip the triple digits, and we'll be in the triple digits Fahrenheit anyway for a while. So I'm looking forward to that. How did you get into astronomy? What do you like to do in astronomy?
So, I've been into science for a long time, all my life. And I actually arrived at planetary science through a pretty circuitous path. I was into geology and paleontology as a kid, but I never got to study geology in high school. So that was the first course I took in college. And I was at a small liberal arts college called Amherst College in Massachusetts. The intro geology course was a field lab course taught outdoors. All our labs were outside with the leaves changing, and it was just absolutely gorgeous. Plus the rocks were amazing. So we there in central Massachusetts is something called the Connecticut Valley, which is a rift valley. It's a failed rift. It's where the Atlantic Ocean tried to open up before it opened up where it is now. And so as a result, you have every kind of rock there. You have sedimentary rocks that are more recent, but you also have stuff that is brought up from below. And all this storytelling is what I really got into. And so it was from that I realized you can do geology in space. And so that's where I'm at. I'm a space geologist. I studied Venus and Mars in grad school and spent the last 20 years explaining space geology to the public via the Planetary Society's website, though now I'm a freelancer.
And you have some pretty cool jewelry on, some ornaments there. I see it on your necklace. What is that?
So one of the things I'm doing now as a freelancer is a lot of space art, and I kind of mix geology and space again. All of the beads that I work with are gemstones. They're, jades and jaspers and quartzes and of various kinds. Nearly everything is quartz, of course. And I create, necklaces and earrings, all of which have a space theme. Some of them are planetary, lots of stuff with the solar system, but I also have a lot of astronomical stuff. Like I make a necklace that's based on the Hertzsprung-Russell diagram. So you get all the different colors of the stars, and they get bigger as you go from red to blue. So
I'm definitely gonna have to get me one of those. Do you sell them?
Check it out. Oh, of course I do. I have an Etsy shop. So elakdawalla.etsy.com.
Okay, there's a push.
Yeah.
Very cool.
I probably shouldn't do that.
No, it's all good. It's all good. Because I definitely want a Hertzsprung-Russell diagram one. That's very when did you get into science writing?
So that happened, I've always been interested in science communication rather than more than science research. I was raised in museums, and I kind of figured that I would wind up in a science museum sooner or later. And so it was with that in mind that I was applying for jobs after finishing a master's degree at Brown University in planetary geology. And I lucked out after spending 1 year very unhappily as an environmental consultant. I found a job at the Planetary Society, which is this nonprofit organization founded by Carl Sagan, Bruce Murray, and Lou Friedman that advocates for space research and exploration.
Yes.
And so I was working behind the scenes for a while, but very early on, I started writing. My first beat was the Cassini mission as soon as it arrived at Saturn, and my professional career spanned all of Cassini's mission, all of the Opportunity and Spirit rover missions on Mars. I've written a book about the Curiosity rover, the engineering, and I'm working on a second book about the science results from the mission. And so I've just been doing science writing for the last 20 years.
Cool. And we'll put some of those links to those books and stuff in the description below the video there. When did you write your first? There you go.
There it is. Yeah. So this one was for Springer Praxis. It's a book about the engineering of the Curiosity mission. And I love figures and diagrams and annotated diagrams. And so this book is absolutely chock full of them. And the most common comment, and the one that I love the most about it, is that people say, I picked this book up thinking that it was going to be kind of challenging to read, but actually it's very readable. And they kept on reading it for the story of the engineering challenges and everything else that go on with the mission. And so now that I've written this one, I know enough about how the rover works that I can write about the science results.
Very cool. I think I know what my STEM orientated daughter is going to get for Christmas.
Outstanding.
or her birthday. It comes up even sooner. So
Mhm.
very cool. When was your first Sky and Telescope article?
Oh gosh, that goes way back. I think, I don't even remember what the topic was, but among the first was one that I wrote about amateur image processors. So these are people around the world who go into NASA and ESA and other space agency image databases. It's traditional now. It's not a very long tradition, but it's traditional now for space agencies to publish all their data and make it available to the public. So you can now, as a member of the public, just download the data, process it, make beautiful images. And so I wrote about this international community that had built up around it. And I gave some information about where people can find the data. And I think I've written a second article for Sky and Tel about that now. It kind of all blurs together. I've been in the business now for almost 25 years. And so I've written a lot of things for a lot of people, but yeah, I've written quite a few for Sky. I love writing for Sky and Telescope. It's like the exact level of audience that I love writing for, where I get to give a little bit more detail than a little more technical detail than most sort of mainstream audiences. And I know that people really eat that up. So it's my favorite thing to do.
Let's eat it up. In fact, let's get right to it on this latest masterpiece from Emily on Venus Renaissance. And Emily, right, take us away.
So I was so excited to be able to write this article. I pitched this article as soon as I heard about the selections of these space missions. At graduate school, I was studying Magellan images from Venus. And the image that you look at right here is a global view of the Magellan radar image data. And that was really the last big mission to study Venus's geology. And that one ended in 1994, I believe, which was actually before I went to grad school. I was lucky enough to have my own funding so that I could keep studying Venus when a lot of other people had to move on to other missions like Mars Global Surveyor. There are some people who had shifted to the Galileo mission to Jupiter. But the Venus community, at least in the United States, hasn't had another opportunity to study Venus data since Magellan. And so it's been a very tough time for Venus scientists. And there's been a lot of attempts to get missions started and a lot of proposals that have not been selected because Venus is just so much more difficult to study than Mars. Excuse me. And that's primarily because of its atmosphere. So we had this successful run of missions that did radar that penetrated Venus's atmosphere to see the surface at we've got global maps, but they're pretty low resolution. They're none of them is better than 75 meters per pixel, which is pretty coarse if you think about it. And the topography, it turns out, as I found to my chagrin in grad school, is actually really lousy. The Magellan topographic data set is just bad, unfortunately. And if there's one other thing that I learned while I was in grad school, it's that topography is really the key to understanding geology and geologic history. Okay. Anytime there's a geologic study on Earth, it begins with a surveyor. It begins with people going out and studying the topography. And then all the other data that you get is mapped on top of that topographic base map. And so we can't progress the way Mars science has progressed until we get a topographic map. And so that's why I was so very thrilled when the Veritas mission got selected by NASA as one of its next Venus missions, because Veritas, the whole point of it is to establish that topographic base map.
And when does that one launch?
That one launches, and I actually have to look at my article, launching as soon as 2027. The launch date is late 2027, and I think it's likely to slip a little bit just not based on anything happening on this mission. It has more to do with the cadence of missions coming out of NASA. Understood. But it will be before 2030 for certain, and hopefully as early as late 2027.
Well, from the desert of no missions, it looks like all of a sudden we have a veritable ocean with 2 missions going.
Yeah, so there's 2 NASA missions that were selected in the same year. That's Veritas, and then Da Vinci, which is a Venus probe that's going to descend through the atmosphere and take data all the way down and land on the surface. But it's actually going to do a lot more than that. And then on top of that, the European Space Agency selected a mid-sized mission called Envision that's going to be launching a little bit later in the early 2030s. And so there are now going to be 3 missions that are headed to Venus in the next decade. And this is going to transform how we understand Venus in, I think, exactly the same way that the Mars Renaissance transformed our understanding of Mars, beginning in the late 90s with Mars Pathfinder, Mars Global Surveyor, Mars Odyssey, Mars Express, Mars Reconnaissance Orbiter. So it's the same kind of suite of spacecraft. It's really very similar, very parallel. And so if you
instruments on it though, right?
There are so many instruments. So the one difference between the state of Venus science now and the state of Mars science as of 1995 is that Venus has had a couple of missions travel to it since Magellan, but they've been focused on the atmosphere. So there are 2 very climate-focused missions that have traveled to Venus. One of them, the mission's over, that's European Space Agency's Venus Express, and the other one is still operating, that's Japan's Akatsuki mission. And they both focused on the atmosphere, on understanding atmospheric circulation, on watching the atmosphere over a long period of time so that we don't just have a snapshot, we understand how its climate varies over the course of its year and how it's actually changing with time. So just like Earth and Mars, the climate is not identical year over year. There are multi-year trends, and there are much longer shifts that happen as a result of orbital changes and other things happening with the sun. And so Venus Express and Akatsuki have studied Venus's atmosphere in great depth. And so they've given us the benefit of this really good understanding of Venus's atmosphere going into these upcoming, more geology-focused missions.
Do you speak Japanese?
I do not speak Japanese. I use Google Translate
really well.
Great. Well, I listen though. I think it's very important to listen carefully to how people pronounce the names and try to do your best to, within the ability of your local accent, pronounce things as they are pronounced by their creators. And so we have some, early in this article, we have some very pretty pictures from both Venus Express at the top of that page that you were just on. So if you scroll up a little bit, you can see this really cool polar vortex feature that we've now observed at both poles of Venus, thanks to Venus Express. It wasn't discovered by Venus Express, but Venus Express found a really unexpected dynamism within this feature. It changes so much. Before Venus Express arrived at Venus, we had this sense that Venus's atmosphere was relatively simple compared to Earth's, for the reason that it's very, very, very thick. And so climatologists and meteorologists thought that the atmosphere didn't really feel the ground below the atmosphere so much. And so since the atmosphere is so thick and the ground was so far below it, it was kind of like a global ocean that it didn't have a bottom that it could feel. It didn't have continents that it flowed around. So it should just be, if you imagine, for those few of you in the audience who have taken differential equations, it was a very simple system to set up. You have your boundary condition at the top is space, and at the bottom is it's just an infinite half space, and that's all you have to worry about to figure out the weather. And it turns out Venus Express found and Akatsuki corroborated that it's absolutely not that simple. Yeah, the atmosphere clearly feels the ground beneath it. One of the first things Akatsuki observed was this standing wave in Venus's atmosphere that forms over Aphrodite Terra, which is one of the taller topographic features on the surface. And so yes, Venus atmosphere definitely feels the ground, and it's dynamic and changes a lot over very short timescales. And so we've got this really rich data set from both of those spacecraft that help us observe and understand and describe that, but we can't explain it. And so one of the interviews that I enjoyed the most for doing this article was with Richard Gale, who's the sort of the science lead for the European mission.
Okay.
And he was talking to me about how they, with Venus Express, they expected to be answering all these questions about Venus's atmosphere. And they got a certain, they made a lot of observations. They learned a lot that we hadn't known before, but they realized that the geology, the surface, was really key to understanding the atmosphere, and that they wouldn't get Akatsuki and Venus Express's results. They wouldn't understand them until there is another mission sent to study the surface better. And so we're going to get to that. We're going to get to the future missions, but looking here in the article, there's a couple more things that that you can see. One of them is this absolutely gorgeous picture from Akatsuki. It's using 2 different ultraviolet wavelengths to see to 2 different depths in the clouds. And this is a trick that most Venus orbiters use in order to understand what's happening at different levels, because ultraviolet light penetrates to different depths depending on its wavelength.
Yeah.
And the same is true for infrared light. You send a camera with different ultraviolet filters, and each one of those images taken through a different filter will actually be seeing the shape of the clouds at a different level in the atmosphere. Now, the thing about Venus's clouds is that, unlike Earth clouds, they are continuous everywhere. There is no place on Venus that is not covered by very thick clouds. And so there is a chance that photographing Venus's clouds, that you would just see a featureless space. And so the fact that you can see any features at all is lucky. And the reason that you can is because of this mysterious ultraviolet absorber. There is some chemical, we don't know what it is. That's why they call it the ultraviolet absorber. It absorbs ultraviolet light. It's what makes the darker, it outlines the clouds in these darker shapes in the atmosphere. Without that, you wouldn't be able to see the shapes of the clouds. You wouldn't be able to track cloud motions, and we don't know what it is. So that's another one of the mysteries, is that we don't know what this ultraviolet absorber is, but fortunately it does help us see these shapes in the clouds. You can see things like how Venus's atmosphere has this strong kind of chevron shape where the clouds appear to angle toward the eastern side.
Yes.
And that's a result of the super rotation of the atmosphere and the different speed. So the whole atmosphere is rotating around the planet once every 4 Earth days. And the wind speed is the same from equator to about sort of Arctic Circle position.
See that.
Yeah, you can see where like that white collar is. That's kind of, so if the wind speed is the same everywhere, then because the diameter of the planet is smaller toward the poles, then the farther from the equator, the wind's traveling faster. And so that's why it kind of outruns the atmosphere at the equator. And so the wind is actually traveling from right to left, from east to west on this, on the globe here, which looks kind of the opposite of the direction of the chevron arrow. Like it's pointing the wrong direction. It's pointing the opposite direction from where the wind is blowing.
Yeah.
Yeah. The other thing you can see in this picture that's kind of cool is a little bit of limb sort of brightening in that blue wavelength, which is a shorter wavelength ultraviolet. And that's for the same reason. That's Rayleigh scattering, actually. It's not, we're not looking at blue light, we're looking at ultraviolet light, but it's the same effect. And so as you look through more of the atmosphere toward the edge of the disk, you're getting, it's getting more opaque in that blue filter image. And so the detail fades out as you go toward the edge of the disk, which is kind of neat.
So I assume the blue is not phosphine.
The blue is not phosphine, I'm afraid, but the European mission will be able to hunt for phosphine. So
we'll be looking for that one.
They will be looking for that one. All right.
Amazing. We don't know what that is yet. That's kind of amazing. You'd think people would take spectra of it and then, do what you do with spectra, figure out what's in it.
Yeah, they have. And, there have been stellar occultations and, Earth radio occultations. There just really haven't been that many, though. And there haven't been spacecraft with the kind of really high resolution, high signal to noise, dedicated ultraviolet occultation instrument that you really need to get those kinds of data. And we're going to get that with Envision. So that's very exciting.
That is going to be so cool. I am looking.
All right. So if you move on to the next page, you'll get to an infographic. And I love my infographics. This one actually grew out of one that I was contracted to do for a different publication that I won't name. And when I gave them all the information, they're like, that's too much for our readers. And I was like, you're boring. So I'm so happy that I was able to get a lot more information onto this one for Sky and Telescope, in particular, the graphs. Yeah.
Yes. So you do your own artwork on these?
I don't do my own artwork, but I do sketch them out. I do the napkin sketches. But I tried the, Sky and Tel has a great graphics department.
Wonderful.
So,
okay.
I actually do make a lot of my own graphics, but Sky and Tel, I'm very happy to have their graphics department do it. Okay. So this is meant to compare the structures of Earth's and Venus atmospheres. And one thing I want to point out to you is that the vertical scale is the same on both graphs.
Yes.
So the mesosphere and the thermosphere, which are these really high upper level parts of the atmosphere, are not too different in location between Earth and Venus. Yeah. And so the really different stuff is happening lower. It's happening in the troposphere for Venus. Venus doesn't even have a stratosphere. It doesn't have the temperature inversion that makes the stratosphere on Earth. Right. And so everything up to 70 kilometers altitude on Venus is troposphere. Yeah, so it's where there's hot air close to the surface, cold air above. You get clouds forming where the temperature drops below the local relative humidity, where the relative humidity increases enough that clouds condense out of the atmosphere. Mm-hmm. And so that's why on Venus, because you have this very, linear, this temperature thing that goes just straight from hot at the surface to cold with no inversion in between, you have this incredibly thick layer of clouds, this sort of almost 20 kilometers thick solid cloud. There is no seeing through that invisible wavelengths. The cloud is divided into lower, middle, and upper layers based on, it seems to be a real division, probably having to do with the size of the droplets and the different species that are condensing and what's solid and what's liquid. Mm-hmm. That's some of the kind of stuff that they've been exploring with Venus Express and Akatsuki, and we'll be doing a lot more detailed exploring of with Veritas and Envision. And then they're going to be getting below it with Da Vinci. So Da Vinci is going to start taking data at about 90 kilometers, so right sort of in the middle of the mesosphere, maybe actually a little higher than that. Okay. And then continuously all the way down, they're going to be taking data on composition and temperature, pressure, wind speed, all kinds of properties of the atmosphere.
Is that a single probe that does a one-shot deal, much like something we might have done on other planets?
Yes and no. So yes, there is only one probe, but there's more to the mission than that. And I'm going to get to that on the next page once I get there.
Okay.
The other thing I really love to point out about Venus's atmosphere is, so we know that, everybody watching this knows that Venus is not a really nice place to live. The surface is very, very, very hot. You can see it on the graph here. It's 700 kelvins. So that's roughly 400 degrees Celsius. It's about double that Fahrenheit. It's really super hot. Okay, so it's hot enough to melt lead. It's very unpleasant. Those clouds, by the way, are made of condensed sulfuric acid. Mm-hmm. So it's nasty, nasty, nasty. But if you go up, if you look on the temperature scale at about 300 kelvins, which is approximately Earth's surface temperature, and go up to 1 bar, which is Earth's surface pressure, you get right to the bottom of the clouds.
Yep.
And so if you had, say, like a balloon or a dirigible, a Zeppelin, mm-hmm. And you were just below the clouds, which is still quite high above the surface, it's 50 kilometers above the surface, you would be below the clouds. You could see the ground optically, although there are hazes, and you would be in a very comfortable Earth-like temperature and pressure range.
Nice.
So people have proposed sending astronauts to Venus you would not be landing them on the surface. You would be floating them just below the clouds where they could see the ground very well. You could send down robots and other things. You could make your observations and never land in the nasty environment. You would be safely in comfortable Earth-like temperature and pressure right beneath the cloud deck.
Oh, wow.
Isn't that neat?
That is totally cool. And you just triggered a very old memory of mine. I must have been like 11 or 12. And I remember picking up this book about exploring the planets, but there was sort of in this phantasm mode. And on Venus, at just what you're describing, there was this whole ecosystem of floatable creatures and floatable spacecraft. Just, all of the biosphere, if you like, was taking place at one bar, 50 kilometers up. That's how.
Yeah.
Yeah,
so,
you just figured that. I mean, that's wild.
People still talk about that. And so if you can imagine a past Venus, that we think that Venus, Earth, and Mars all started out a lot more similar than they are today. And so there could very well have been an ancient Venus, and maybe even not so ancient, maybe less than 1 billion years ago, which is, a long time, but it's not what geologists call ancient, or at least planetary geologists.
Right.
And so if there were a biosphere on Venus, and then things got bad, the place where you would look for any surviving life forms would be in the clouds, because that is where anything that evolved in a watery environment would now be able to live, in theory. Although, again, those clouds are concentrated sulfuric acid, which is kind of not very nice to organic molecules, but we can dream and hope, and we can certainly look. So that's something that will be done in the future.
Awesome.
All right.
Very cool. All right. Blow out, and there's I guess not.
Yeah, here's another Akatsuki image. And so this one is it's infrared. It's sort of like a mid-infrared image. So instead of looking at reflected light, which is what the ultraviolet image was previously. So we were looking at sunlight, ultraviolet sunlight being reflected off the clouds. This is emitted light. So this is the light, the infrared radiation from Venus's heat. It's not the heat of the surface, it's the heat of the lower atmosphere. So it's the glow at this wavelength, it's the glow of how hot the lower atmosphere is. And so what you're looking at is the clouds being silhouetted against the heat from the lower atmosphere. So where it's brighter, the clouds are thinner. Where it's darker, the clouds are thicker. And so again, that makes sense you can see the limb darkening toward the edge. You're looking through more clouds, and so it gets darker. And then you can see on the, just past the evening terminator there's this doublet, this kind of feature where we're lower in the atmosphere now than the clouds we were looking at on the ultraviolet image. And you can see there's a thick sort of bow shape or parentheses shape of thick cloud. Then there's a rarefaction, a thin cloud, and then there's sort of an echo, a thick cloud. And this is a gravity wave. So this is the atmosphere piling up behind the elevated terrain on Aphrodite Terra, and kind of piling up. And there's wave action happening in the atmosphere here.
Very cool.
And Akatsuki has seen this over Aphrodite Terra. And this was a huge surprise that it was such a stable feature that was clearly feeling Aphrodite Terra, which is, anywhere there's clouds, you are looking at the surface is 50 kilometers below the clouds at least. So that's a long distance, 50,000 meters.
And that still goes to your point that the surface matters.
The surface really matters. Yeah.
Right.
Yeah.
Very good.
And so Venus Express tried to look at the surface as best as it could. Venus Express was a very low-cost mission. So the Europeans did something really clever in the 2000s, which is they had built this really big, expensive spacecraft, Rosetta.
Oh, yes. Okay.
And then they had the ability to buy spacecraft buses that were the design of another Earth observing spacecraft they had. And so they could repeat the design of the spacecraft bus and its solar panels and use it several times. And so they reused this, I forget what the Earth orbiting mission was, but they came up with Mars Express and Venus Express.
Got it.
And if you look at Mars Express and Venus Express, the spacecraft look quite similar, except that the Venus one has smaller solar panels. They just have like one less panel on the end because they're a lot closer to the sun. They don't need so much solar panel to generate the same amount of power. And so Venus Express was the last of these. It was the lowest budget. And so given all of that, it's amazing what they managed to accomplish with it. It's a pretty small scientific package. The imagers were not, the highest resolution or the most spectral resolution compared to a lot of other spacecraft, but they stayed at Venus for a long, long time.
That helps.
And so they made up in temporal resolution a lot for their lack of spatial resolution. So they could do things like see at the bottom of the page here, where there were changes over time in the emission from the surface and the infrared color from the surface. And that could mean a couple of different things. It could mean that there is a warm glow from an actual volcanic eruption, which I think is the most exciting possible interpretation of it.
Definitely.
It could mean that that there is a relatively fresh flow, maybe not one that happened while Venus Express was there, but that it's been chemically weathering over time, so that when the minerals, when you get a fresh flow and then it starts breaking down, because have I mentioned that there's sulfuric acid in the atmosphere, and it will oxidize the minerals and change their composition. And so what we're seeing here could be one of those two things. It could be something else entirely. But the point is that Venus Express was there for long enough to see changes on the surface.
Right.
And so, yeah. And so we would like that to be, it would be wonderful if Venus Express had been able to prove that there was active volcanism on Venus, because that would be really exciting. It didn't prove it, but a lot of the data that it got, we'll just say it was not inconsistent with active volcanism on Venus.
Oh, that was so professionally said of you.
So anyway, it's worth following up on, which is what Europe is doing with the Envision mission. And so we had this, we've been learning amazing stuff about Venus. We've not had an American mission successfully selected for Venus since Magellan. Right. It felt like it's been feeling like the Venus community's time for a long time, but they've been proposing missions, never selected. It was extremely frustrating. And it seemed like it was never going to change until astronomers arrived to save the day. And so I'm talking about exoplanet astronomers. So the rise of exoplanet science in the last 20 years has been meteoric. And to use the term,
go ahead.
To use the term in a way that actually irritates, I know, astronomers, because of course meteors fall, they don't go up. But anyway, the point is that a ton of astronomers have moved into studying exoplanets, and exoplanets are this topic that is obviously at the intersection of astronomy and planetary science. You have to be an astronomer to study exoplanets because they're very far away. But you have to have planetary science in order to understand what you're seeing. And there is no better way to understand very distant, low resolution data than to be able to compare it to something that is much closer to home. And so the exoplanet community really needs better data on Venus as well as Uranus and Neptune, because Venus is an Earth-like planet. Venus has the same size as Earth. It's at a similar distance from the sun. The composition is the same. The mass is basically the same. And yet it's clearly not a hospitable place for life. And so exoplanet astronomers want to be able to differentiate the Venus-like planets from the Earth-like planets, so we can try to understand how common Earth-like planets are in our galactic neighborhood. And so the exoplanet community has been advocating for Venus missions and Uranus missions and Neptune missions. And that appears to be what finally broke the jam for American Venus missions, was the increasing connections between the study of Venus and the study of exoplanets. And so there was actually a first meeting a couple years ago called Exoplanets in Our Neighborhood. And it was about it was about bringing together exoplanetary astronomers with planetary geologists and climate scientists to start trying to come up with the research questions that needed to be answered in order for exoplanet scientists to be able to understand their results better. And I was able to go to that meeting. It was a marvelous meeting. It really felt like it breathed fresh air into what had been a pretty stagnant American Venus community. And so it was very exciting. And I think it was one of the things that contributed to these two NASA missions being selected.
Multiple communities is always a good thing.
Absolutely. Yeah. And exoplanets have been doing that for a lot of people. So the Venus community has set up, has articulated a set of goals for the next couple decades of Venus exploration. And they're written about on this page. There's three goals. The first one is to figure out what Venus looked like early on, basically Venus geologic history, to understand how similar it was to Earth, whether there was a habitable environment there or not, and what happened to make it the kind of hellhole it is today. The second thing is to understand the composition and motions of the atmosphere. We've gotten a very good head start on that with Venus Express and Akatsuki. And now the next generation of missions is asking more specific, more targeted questions with instruments that are designed to focus in on the questions that are going to help follow the changes and shifting motions in the atmosphere much more closely than we were able to with Venus Express and Akatsuki.
And what in the heck is that mysterious absorber doing? Exactly.
What is a mysterious absorber? That kind of thing. And actually the third goal, I'm sorry that I kind of mixed up the first and third goals. The first one is about past habitability, climate change. The third goal is about geologic history. And this shifting understanding of whether Venus had some kind of global catastrophe that completely erased all its craters and caused its surface to acquire the appearance it has today, which is the post-Magellan view, or whether it's been more active and is active today. And we don't know the answer to that. So that's a really big fundamental question about Venus's history. And so those are the main three goals. And these three missions are really, really going to help us understand that. So I'm actually going to skip over these two images for now, because I want to go to the next page first, and we can come back to those two. So the next page is showing you a timeline at the bottom here. So that timeline shows you when each of the missions is going to be operating at Venus. And so you can see that Veritas is shown launching toward the end of 2027. Cruises are fortunately very short to Venus. So that's the light colored bar there. It's very quick to get there, relatively easy, even shorter than Mars. And so, but it can be hard to break into orbit because you're going very, very fast, because you're so close to the sun. And so most missions will use something called aerobraking, where you skim into the atmosphere and use the very, very tenuous uppermost atmosphere to exert pressure on your solar panels that slows you down. And so there are many, 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 many orbits devoted to aerobraking and gently circularizing your orbit until you arrive in orbit. And so Veritas is going to do a first, more distant set of science observations to get a kind of global map from an early orbit in early 2029. It'll provide a base map for Da Vinci and a base map for its own future observations before it continues aerobraking down into a much smaller orbit for its topographic mapping. And then once it arrives in that orbit, I think it's 4 Venus years, if I'm not mistaken, 4 or 5 Venus years of its science mission, where it'll be mapping, and Veritas is going to do global mapping. So I feel like Veritas is very, very similar to Mars Global Surveyor. Mars Global Surveyor carried 3 main instruments, actually 4. It was a topographic mapper. It mapped the global surface composition at low resolution. It actually mapped it in low resolution with 2 different instruments. One was a neutron spectrometer, one was an infrared spectrometer. And then it had sort of a wide angle weather mapping thing. And so that's the one thing Veritas doesn't really do, because it doesn't need to, because we've had all these weather mapping spacecraft there for a while, and hopefully Akatsuki will still be working when Veritas gets there. Okay, so that's Veritas. That's its prime mission. It's going to be amazing. It's going to give us these global maps like the ones from Mars Global Surveyor that revolutionized our understanding of Mars. Mars Global Surveyor finished its basic global map in like the early 2000s. And every single spacecraft that's gone to Mars since then has tied all of its science to that global topographic map. And so it multiplies the value of all those other science data sets, because you can relate, you can do geographic information systems, you can do spatial relation between data sets and understand how things are correlated with other things. And that really helps you get at the geologic history of Mars in a way that was not possible before. Veritas is going to do the same thing for us for Venus.
That's just so great.
Yeah. Okay, so then Da Vinci launches a couple of years later, and Da Vinci is primarily a probe. So I think of Da Vinci as kind of like the Huygens mission for Titan. So it's an atmospheric probe. It's focused on the atmosphere. It takes data as it goes down and relays it to Earth directly. I'm sorry, not to Earth, to Da Vinci actually, like Huygens, has a relay spacecraft. So Da Vinci has this flyby craft that will be receiving all the data and storing it for later transmission.
Okay.
And so it's going to be taking all that detailed data about atmospheric composition and cloud composition and motions and temperature and pressure. And it has a camera that as soon as we break through the clouds, we'll start imaging the surface, and we'll image it all the way down. It's going to be a really, really, really cool mission when it descends in mid 2031. But that's not all it does. So before the descent, it actually will do 2 flybys of Venus in order to set up the geometry. They want to be descending with the sun right behind them, so that they've got the best solar illumination angle.
Got it.
And during those 2 flybys, they are going to be flying over, basically approaching Venus along the same geographic location that they'll be descending later. So the orbiter, or the flyby craft, has cameras and other instruments that are going to be taking this data set, looking all the way down at the surface. They'll be able to use it to fine tune their landing location. They'll be doing that on 2 flybys. So we get all of that data leading up to the descent. During the descent, they'll be, primarily be serving as a data recorder, but the descent will set up another flyby. And when they come back around, they could actually go into orbit. And so their flyby craft could then become another Venus orbiter.
Right.
Now, it's not as cool a science orbiter as Veritas, but it has these other imagers, cameras that Veritas doesn't have.
Right.
And it's that having 2 spacecraft at a dynamic planet like Venus at the same time is always better than 1. In fact, it's more than just 2. It's like having 3 missions, because you've got the 2 spacecraft and you have the way you can intersect their 2 data sets.
Yeah.
So that's going to be very cool. And then finally we get to, so Europe is thorough and bureaucratic. They move a little more slowly, but very, very thoroughly and systematically. You don't get the kind of announcements and cancellations and stuff like that you tend to get as much with NASA. Yeah. And it's funny, Japan is actually, it's like Japan is to NASA as NASA is to Europe in terms of the speediness of their missions. Anyway, I digress. So we get Envision. Envision launches in mid 2032, probably, although that can change. And then just like Veritas, they'll do aerobraking for a while, and then they go into a long science mission.
Wow.
And when Veritas was first announced, it was actually, I'm sorry, when Envision was first announced, it was before Veritas.
Oh, okay.
They thought they were going to have to do the global topographic map that we didn't have. But because Veritas will be there first, Envision doesn't have to do that, which is great because they can get to higher resolution. And so they can take the Veritas map and say, okay, what have we learned about Venus? What are the highest priority targets? And we can focus our efforts on imaging those targets at higher resolution. And we can also image them repeatedly so we can see if in fact they are changing with time. So they can focus on possible centers of volcanic activity and see if they can catch before and after images of volcanic eruptions, of new lava flows and things like that,
Cool.
with both their radar imager and their infrared imager.
Okay. Yeah.
Plus they have other instruments that will be continuing the Venus Express experiments of looking at the atmosphere. Veritas and Envision will be carrying identical, at least one of the cameras that's on Veritas is identical to one of the cameras on Envision, which is not something that has been done very much in planetary science, but it's really common in Earth science. And so these climate observation instruments have a very long tradition, especially in Europe, of you launch one spacecraft after another in a long series, so you have a continuous climate record. And so we're going to get that with Veritas and Envision, that this infrared instrument that can see both clouds and the surface is going to have this lengthy, at least a decade of continuous observations of Venus's surface and atmosphere and how they change with time.
Awesome.
So if you go back a page now, you'll see why I wanted to skip briefly. So at the top, this little infographic is just emphasizing how only the Vega and Venera landers ever got to study most of the atmosphere. Pioneer Venus probes cracked, they ended just below 20 kilometers above the surface, but Da Vinci is going to get it all the way down. So Da Vinci will be the first since the Soviet space program to actually get us data from the lower part of Venus's atmosphere. And it's so important to have that one in situ measurement of composition and dynamics and pressure and temperature and all those things, because just one profile can establish ground truth for meteorologist models of the entire atmosphere. And so this will help meteorologists understand and correctly simulate what Venus's atmosphere is producing in terms of chemical species, in terms of aerosols and dust, and the different compositions and how that changes with altitude. It's going to be incredibly important to understanding Venus's climate and weather.
Absolutely. How about on the surface? I remember, if memory serves right, I remember the Venera landers, when they hit the surface, they lasted all of like a few minutes, enough to get a few images, which were pretty famous, but just a few minutes. How long is the anticipation for the Da Vinci probe on the surface? Is that
not at all? And unlike Huygens too. So Huygens was designed to float in Titan lakes. And so it wasn't expected to last a long time on the surface. It actually surprised us by lasting for hours. I don't think, I actually don't know what Da Vinci's prospects are. I do know that it's going to be hard for it to communicate once it tips over upon landing. Oops. So, and it's not really designed to survive the intense temperature and pressure of the surface environment. So regardless, it's not going to last long. Okay. I don't know if it'll communicate at all once it reaches the surface, but so it's very important to get its data as it is descending.
Yeah, you need some bandwidth there.
Yeah, that's right.
Very cool. Very cool. And
so now scrolling down, this is, I think, the graphic that the Veritas principal investigator is the most excited about, Sue Smarker. Because it shows you the top image shows you how well we could see the island of Hawaii if we had Magellan resolution.
Right. Wow.
And the bottom image shows you what we're going to get from Veritas's radar instrument over a feature of similar size.
Orders of magnitude.
Yeah, you can really see how the top one, you wouldn't be able to interpret. You wouldn't know what's there. Now, on Venus, volcanoes are big enough that you can see them at Magellan resolution, but presumably there's lots of volcanoes we can't see at Magellan resolution. So not only are we going to see those big ones in better detail, we're going to see lots and lots of smaller ones, and we have a chance of seeing change over time because the scale is so much smaller. Yeah.
That is just lovely.
Yeah, so I'm so excited for a modern radar instrument at Venus. Exactly. I mean, Magellan was great, but it was just one mission. Magellan was basically like the Viking orbiters for Venus. They gave us our first really good global look. They helped us understand what questions to ask. And we haven't had that second generation yet, unlike Mars. Mars is now onto its third generation of spacecraft. This is like the second generation, beginning with the climate orbiters, which were very important. And I want to mention, I'll mention those again because, you know, the American scientists have this habit of saying, oh, we haven't been back to Venus since Magellan. It's been this huge drought. It's been awful, 30 years of no missions. And Europe and Japan are over there going, hi.
Hello.
Venus Express lasted for a decade and, you know, Akatsuki's still there.
Still there, yes.
Yeah. Still doing great science. It's just that there hasn't been geology.
Right.
And so, and American planetary science really grew out of the Apollo program, which was, you know, at least scientifically, it was about doing field geology on the moon, even though we all know the Apollo program wasn't really motivated by science. It was motivated by politics, global geopolitics, that kind of stuff.
As long as let's do some geoscience, okay.
Right. And so the first American planetary scientists were literally field geologists who were brought on board to train the, you know, Apollo flyboys, all these Air Force pilots, how to recognize a rock. And my advisor at grad school is actually one of those guys, and he tells me, or he tells a story about how exciting it was when one of the Apollo 11 astronauts looked down at his feet and said, "Hey, that looks like a northicite." Oh, he was like, "Yes!" He was listening in class.
Whoa, that's pretty good.
Yeah. Good. So he was tickled by that.
Yeah. And then, you know, just throw some local stuff. So here in Arizona, there's a Bellinger crater, meteor crater, and they have a number of things there that show that the Apollo astronauts, flyboys, were down there training, walking around, and they even have, like, you know, the size of an Apollo astronaut down at the very base of the crater. So if you ever go to Bellinger crater, meteor crater in Arizona, check it out. It was a training ground for Apollo, where flyboys got some geology names. Yeah,
I've been to Barringer, and I've every time I fly over it, I always look for it out the window and take pictures. It's pretty cool to see from the sky. All right. So we can go on. I think I haven't talked about the instruments in detail. I think it's better to just read the article to get all the details of how the instruments will operate. But this map up here on page 19 is kind of cool because it shows you that this is basically what Magellan has given us. So Magellan gave us this global view. And since Magellan, geologists have been mapping on the Magellan data, trying to understand how the geology differs from place to place, what the history is. And so they've mapped all of Venus and divided it into different kinds of terrain. There's tesserae, which are these radar bright, heavily fractured, high standing, like they look very crunched up geologically. There's been a lot of history that has happened to the tesserae. And then there's coronae, which are these circular, ridgy features that they're kind of enigmatic in origin. They may have to do with convection in the mantle. We don't really know.
Yeah, fair enough. I agree.
There are rift valleys, there are ridge belts, which are like folded mountain belts. There are lots and lots of dark, flat lava plains, which seem to be younger than everything else for the most part, and they have wrinkle ridges across them. And so this map shows you that Magellan interpretation, and the places where there are color identify locations where the Envision team has looked at the research and in many cases participated in the research, and have prioritized a lot of these areas for looking at high resolution with their mapper. And so they've got like this preliminary list of places they want to image at least once, and some of them presumably multiple times in order to see if they're still active.
You have targets.
Yeah.
Very good.
Yeah, and so that's the last image in this. The other thing that was really fun that, you know, so I did 3 interviews for this. I've written a lot of sky and telescope articles. My first several were kind of what I called in college connect the quotes, you know, where you do a bunch of interviews and you pull the best quotes and then you write some text in between them, and then that's your article. And then I stopped doing that because after I have scientific expertise, and I found that I could put a lot more information into an article
Yeah.
if I did the interpretation myself.
Cool.
And so I stopped relying on interviews so much. I might do an interview in order to get some tips and clues and important information, ask some questions, but my articles tended to be less quote heavy.
Okay.
But for this one, because it's about future missions and it's about what went into designing a mission, the choices they wanted to make, this was all stuff that I didn't really know. And so I got to go back to the basics. I did 3 interviews. I interviewed Sue Smerkar, who is the principal investigator on Veritas. I interviewed David Grinspoon, who's a team member on Da Vinci, and also I think a frequent author and columnist for Sky and Telescope.
Yeah.
And I interviewed Richard Gale, as I mentioned before, who is the kind of science team leader. He doesn't have an official title yet, but he leads the science currently on Envision. And all 3 of them talked toward the end of the interview about how much of a relief it is for the Venus community that these 3 missions were selected, because for the longest time, there's been, first of all, there's been fighting over very limited funding for Venus research, because there is no active mission sending bucks towards scientists, bucks or pounds or euros or whatever.
Sure.
Yeah. And also everybody was forming teams to propose missions, and therefore in competition against each other. So they're all keeping secrets from each other because they didn't want to let people know their ideas for their mission designs. And so there's a lot of acrimony there. It was very uncomfortable.
Situation. Yeah.
Yeah. And so everybody is just so happy that they're all on the same side again. And so now there's all this collaboration, and Veritas knows that they're laying the groundwork for Europe's mission. They're laying the groundwork for Da Vinci. Da Vinci is going to be feeding back into Akatsuki and Venus Express science. Everything is feeding forward to Envision. And so it's like, and plus, of course, there's more money flowing in, which always makes people happier. But it's the amount of relief, and how everybody is friends again. They're all able to talk openly about their missions and talk about a future of Venus science is just, it's such a breath of fresh air. It's so exciting. And so I think that was, it's something that, the last couple of years have been really rough here on Earth. And to have this shift in mood in Venus science, I think has been just really, I think, emotionally beneficial to this large group of planetary scientists, as much as it will benefit science. And so it's just been, as soon as these missions were selected, I immediately fired off an email to my editor saying, please let me write this article. And fortunately I was able to, because I'm just so excited I'm getting back into this community myself. I was a Venus researcher as a brand new baby scientist, and I'm just so excited to be getting back to it.
That's so cool. That's so cool. Emily, thank you so much for walking us through this awesome article.
You're very welcome.
And usually at this point, we talk about the future, but this whole thing was about the future.
This whole thing is the future. And really the only other future you can talk about is extended missions.
Oh.
So I've already mentioned one extended mission, which is that if everything goes well with Da Vinci and the descent goes well, the flyby craft, the next time it comes around, it could enter orbit at Venus, which would give us another spacecraft at Venus, which would be super cool.
Yeah.
And for both Veritas and Envision, there is no reason to think that the solar panels are going to come off as soon as their prime missions are over. And so with Envision, that just means more of the same, because their main thing is looking at change with time. And so the longer they last, the better their science gets. Yep. With Veritas, I think it's a little bit more, there are some more options open. Mm-hmm. You could change the orbit. I don't know how much leeway they have with this, but with missions that study topography, the closer you get to a planet, the higher resolution topography you can get. And so they could try to get closer to Venus and do higher resolution topography, higher resolution gravity studies. Of course, the atmosphere gets in the way of you getting too close to Venus, but that would be one thing you could consider besides just adding more of what they've already done with Veritas. So not that it wouldn't be useful to do more of the same with Veritas, but NASA tends to look grimly on extended missions that are just more of the same. They want you to be asking a new question, because if your prime mission was successful, then you have answered the questions from your prime mission. And so you need to have new experiments with the same instruments in order to justify the expense of an extended mission. And so I can see something like that, or something collaborative with Envision setting up for the Envision mission that would help Veritas win a mission extension. Anytime you ask a principal investigator about mission extensions, though, they're like, no, we got to get our prime mission done first. We're not asking for anything else. So.
First things first.
Yeah, exactly.
And you know, on the happy side, I'll be an optimist and say, okay, so maybe there'll be a fourth mission in the 2030s. There'll be a new one we don't even know about yet. So
absolutely. Well, I want my balloon mission to Venus. I want to get a balloon. A lot of people have studied this. Get a balloon below the clouds, float around in the atmosphere, take regular old-fashioned visible light optical images of the surface that we all can understand, and then do cool stuff like that. I also want the exoplanet scientists to win and get us missions to Uranus and Neptune, and then we'll finally have all of the planets of our solar system properly explored.
Yeah, I gotta say, for those who are teaching something like an introductory to solar systems class or something along those lines, it will be so refreshing to get some new Venus missions, right? Because
yes,
showing the same ones for a while.
Yeah, but at least you have the beautiful images, especially from Akatsuki. Those images are so gorgeous. And so you can at least, those of you who are getting tired of showing the same Magellan images.
That's what I was referring to.
Yeah, make sure you look up Akatsuki because those pictures are beautiful.
Okay, awesome. Very cool. Emily, thank you so much for walking us through your article and adding 1.5 tons of extra material. That was great.
Glad you enjoyed.
And that'll do, everyone. And I hope this makes your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.